It is.
And that it takes the
It does.
We don't want to do that. Oh no. Happy late Veterans Day.
Stinks.
Beat Army, right?
You were worth it.
Huh?
You were worth it.
Much appreciated.
That's been my response.
Oh. Do you use a foundation? Sometimes, but when I do, I use the Estee Lauder one. I don't. This one? Which shade though?
Okay. Homework 6.2, real quick. Let's talk. I do think there were some questions on there that may or may not have been covered very well in class. Most of it about independence and dependence. For instance, if you want to know, or one about the rain in Orlando, right? Probability of it raining in Orlando and the probability of it raining at Disney World, which is really close to Orlando. What's the probability of total? It doesn't matter if it's independent or not. If you still want the total amount of rainfall, you just add the two up. Okay. But hopefully, from looking at some of these, right, they're like this was highly missed, like 32% only got it right, but it only still took 1.8 attempts. So most of you got it on the second attempt. The goal is for you to learn something from the homework more than anything else. Hopefully you're not just guessing and choosing and that type of stuff, right? Learn from your homework. Learn from it. It's not there for you just to get the easy points. I don't care if you get the easy points. I want you to learn from it, okay? All right, 6.3. 6.3. It's entailed. It's detailed. It's full. However, I did much better the second time than the first time. Come on. Come on. Okay. There we go. Focus. We're going to talk about binomial and geometric random variables. Okay. All right. So, here we go. Come on. My connection is horrible today, obviously. Sorry. Binomial distributions. Still not working. Okay, now we're going to go maybe. All right, here we go. The other day, guys, we tossed a coin 3 times. We tossed a coin 3 times. We counted the number of heads. Okay? You could get 0 heads out of those 3 coins. You could get 1 head out of those 3 coins, 2 heads, or all 3 heads out of those 3 coins. Y'all kind of remember that, right? The value of X was the number of heads. So you could get 0 heads. The only way to get 0 heads is you had to get tails, tails, tails. And there was only one way out of those 8 that showed up that was tails, tails, tails. You could get 1 head, and there were 3 ways to get 1 head. It could have been the first one, it could have been the second one, it could have been the third one. Or you could have got 2 heads, which is the same probability as 1 tail, okay? Or we could have gotten all 3 heads, which only happened once. You guys kind of somewhat remember doing that. This is the probability model of tossing a coin 3 times. Okay, we can figure out the mean of that by doing this times this plus this times this plus this times this. We can figure out the standard deviation by doing that formula of standard deviation, right? And I said, boy, it's a good thing we're not doing this 20 times, because if we were, it would take us forever to list all this stuff. Good? Okay, so now let's look at this. Suppose I'm going to flip this coin 6 times. Okay, so if I'm going to flip that 6 times, we know that there's 2 possibilities for the first one, 2 for the second, 2 for the third, 2 for the fourth, 2 for the fifth, and 2 for the sixth. And if you multiply all those together, that gives me 256 different combinations, right? 256 different combinations, a whole lot more than if I just tossed it 3 times. And if I wanted to know exactly 4 heads, so there's that 256. Well, exactly 4 heads, if I started listing these things, it's the first 4. It could be the first 3 and the 5th. It could be the first 3 and the 6th, the first 3 and the 7th, or the first 3 and the 8th. Or, right, we just start listing and listing and listing, and this would take forever to list all of those possibilities. Good enough? No, I ain't doing it, right? Not going to do it. Nope, nope, nope. There's got to be an easier way, and so that's what we're going to be talking about today, okay? All right, so let's learn about this. Many random variables seen in practice account to the number of successes in independent trials, such as the number of doubles in 4 rows, the number of patients out of 10 patients that have type A blood, the number of defective items in a sample of 20 items. It's either success or failure. It's either good or bad. It's either a yes or a no, okay? These are called binomial situations because they have a success and they have a failure. They have a success and they have a failure. They have a yes or a no. It's either a heads or a tail. It's type O blood or it's not type O blood. It's a green car or it's not a green car. It's success or failure. Do understand that failure, or I should say success, sometimes might mean a failure. Like you wanted to count the number of defective products, that would be a success. Just kind of understand that, okay? So those are binomial distributions or binomial information. Here's a binomial setting. You need to know this. You need to know if it's a binomial setting or not. And if you can recognize it's a binomial setting, that is 90% of the issue, recognizing it's a binomial. So first of all, it has to be binary. It has to be binary. It has to have the success or failure. It has to have the yes or a no. It has to have a good and a bad. It has to have a heads or a tail. It's got to have one of those. It has to be binary. If it's not binary, there's no way it can be a binomial setting, okay? The next thing is each trial must be independent of the previous. Each trial must be independent of the previous. If it's not independent, and of course, it cannot be binomial. So it has to be binary. It has to be independent. You have to have a fixed number of trials. That's the biggest one that sets these things apart. That's my biggest clue that tells me it's going to be a binomial distribution. We're flipping a coin 20 times. We have 5 children. We have 200 trees. It has to have a fixed number. Okay? And then the last one is it has to have the same probability, which to me, this one has to make sense because if they're independent, they have to have the same probability because that's the definition of independence. In order to be independent, the probabilities have to be the same. If the probabilities are the same, then they are independent. So those two have to happen. I don't think I've ever seen an instance where they're independent or not independent and not have the same probability, vice versa. Our book, a lot of teachers call this the bins. The bins. That somewhat helps you decide bins because it's very likely that they will ask you, is this a binomial setting or what type of setting is this? And if it is, it has to fit all 4 things. If it fails one of those 4, it's not. If it fails one of those four, it's not. Okay. Pencils, y'all okay? Everybody good with those four things? Check the bins. Tell me if this is a binomial distribution or not. Genetics says that the genes of children received from their parents are independent from one child to another. Independent. Each child, a particular set, has a probability of 0.25 of receiving type O blood. Same probability. Suppose these parents have 5 children. Fixed number. Count the number of children with type O blood, and that is you either have type O or you don't have type O. Y'all okay with that fitting a binomial distribution? Okay? Recognize them. Yes, that one for sure is one. It fits all 4 things. It's binary. You have type O or you don't have type O. It's independent, and it said it was independent. Independent given. The fixed number were 5 children, and it's the same probability every time. Okay? Next one. I'm going to shuffle a deck of 52 cards. Shuffle a deck of 52 cards. I'm going to turn over the first 10 cards and count the number of aces. Success, failure? It's either an ace or not an ace. Is it independent? No. When I turn over that card, now what happens to the next card? You've changed the probability of that next card. So these are not independent. And because they're not independent, they don't have the same probability. So it fails 2 of those things. We do have a fixed number of cards, and we do have success or failure, but we don't have independence. And as soon as we don't have one of those, it cannot be a binomial distribution or binomial setting. All right, so now I'm going to shuffle the deck of cards, and I'm going to turn over the top card. And then I'm going to put that card back in and shuffle the cards and turn over that top card. So now do I have independence? Now I got my independence. I'm going to repeat this process until I get an ace. Binomial setting. I don't have a fixed number of trials. I don't have a fixed number of trials. If it said I would do this 10 times and count the number of aces, then that would be a binomial setting. But this just says I'm going to do it until I get an ace. That is not a binomial setting. It's binary, yes. It is independent, but I do not have a fixed number of trials. Okay? Beautiful. Last one. Oh, no. So now let's talk about the blood scenario. So bear with me on this one. I'm going to do it. Second time I did this yesterday, I did much better. So just kind of bear with me a little bit. We have a binomial random variable. The possible values, this kind of confuses students at first. The possible values of X, or the number of kids with type O blood, starts at 0. And that's kind of hard for students to understand. The probability of 0, well, that's the probability of none of them happening. That's the probability of getting no tails. There is a chance of it not happening. All right, there's a possibility if I have 5 children of none of them having type O blood. There's a possibility that all 5 of them have type O blood. So that possible values of X are always 0, 1, 2, 3, 4, up until the number of trials I have. So kind of remember those type of things, okay? Remember that 0 is a possibility. All of these start with 0 and go up until however many, whatever the maximum troubles or possible there are. We have 5 children. What's the probability that exactly one of those 5 have type O blood? So just kind of watch, soak this up. Don't write anything down, okay? All right, so let's just do this really quickly. I got 5 children. 5 children. 1, 2, 3, 4, 5. I want the probability that exactly one of them has type O blood. Well, let's just say the probability that the first one is type O blood. This is 0.25. That's the probability that he got type O blood, and that means rest of them did what? Did not get type O blood. So this has to be a what? 0.75, 0.75, 0.75, 0.75. Just soak this up, but if you don't follow along, don't worry. It's not that big of a deal, but it's kind of neat how this works. So that's the probability of what? The very first one having type O blood. But this 0.25 could be here. And this 0.75 could be here, and that would be the probability of the second one having type O blood. Or that 0.25 could be here, and this 0.75 be here, and that would be the probability of the third one. But that's still all the probability of what? One child. So all 5 ways of this happening, because there's 5 ways of this happening, 1 way, 2 ways, 3 ways, 4 ways, 5 ways, that's the number that we got to try to figure out. How many ways can this happen? Okay? Because I think it's understood for us to understand at least this 0.25, there has to be one of those cats that has success. And then the 0.75 has to be the other 4 kids that don't have type O blood. Okay? It's this number here that's a little bit hard to come up with. Because if I wanted 3 of these, that's where we had to start listing all 3 possibilities. And I don't want to list them all. I just want to know what that number is. However, I would understand that 0.25 would be to the third, and the 0.75 would be to the second. The 3 that do have type O and the 2 that do not. I just got to try to figure out how many ways this can happen. Y'all kind of somewhat follow all that? Again, just soak this up. This is the binomial number. That's that binomial setting. It's that binomial number. You guys that took pre-cal, you found that binomial number by using Pascal's triangle, or you found it by using the binomial formula. In stats, we don't use Pascal's triangle. We're going to use binomial formula, and we're not even going to use the binomial formula. We're going to use the binomial distribution because it's going to do all of this with 1 step. Follow? If you don't follow, follow starting now. Okay? So here we go. We can always list them. Here they are. That's the first one. There's the second one. There's the third one. There's the fourth one. There's the fifth one. Then what we learned about independence. Independence means if they're all independent, you just have to multiply those together. And so it would become 0.25, 0.75, yada, da, 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 da. That's doing the same thing over and again. There's the probability of exactly 1. That would be 5 ways. Again, all this is just repeating what I just talked about. Okay? This is the number of ways to get 1 child. This is the probability of that 1 child having success and the 4 failures, if you will. Okay? Again, our big number, this is easy to come up with and this is easy to come up with. This is not. It's not that hard in our class now because we have calculators that do all that for us. So here we go. What if we had 8 children and I wanted the probability of 3 of them having type O blood? Well, first of all, I know for a fact that 0.25 will be to the 3rd power because there's 3 of those cats. And there's 0.75 to the 5th power, the other 5 cats that don't have type O blood. The problem is, how many ways can that happen? And so that's what we're going to talk about for the next 5 or 6 to 8 minutes. Good? Okay, here we go. The number of ways to arrange this is called the binomial coefficient. Again, you don't really have to worry about it as long as you know it's a binomial setting because the calculator is going to do it all for you. This is the part you need to know. You don't need to know this. You don't need to know this. You don't need to know any of this stuff. That's just for my mathematical nerds that like to figure it out. But all it is a combination. Maybe you've heard of combinations and permutations before, where you have, 8 children, and we want to choose 5 different ways from those 8 children. That's a combination. Again, you don't need to know any of this stuff, but it's just for my mathematical nerds that kind of want to see how it works mathematically. And me. Okay? But if you don't follow, don't worry about it because you don't need to know it. You sure don't need to know this formula. You just need to know this part right here. And this part right here means this right here, but you don't need to know that. Bear with me. Here we go. Boom, boom. This you need to know. You need to know the binomial formula, but you don't have to have it memorized. Why? Because it's on the formula sheet. And so this is what the binomial formula says. It says the probability of X, and X is the random variable. X in this particular case would be the number of children with type O blood. It could be the number of heads that show up. It could be the number of pine trees. Equals K. In this particular case, this would be X is equal to 3. 3 kids with type O blood. I think we flipped that coin 6 times and I wanted 4 heads. So this would be 4. flipping heads. Okay? Then this NK, don't try to write it any fancy. Just write an N and put a K underneath it. Don't try to make it a fraction. Don't try to make it a comma. Don't try to do anything else to it. It's just NK. N is the number of trials. N is the number of trials. And K is the number of successes. And if you know that N is the number of trials and K is the number of successes, this is all you're going to have to write. And then P is the probability of success. That is the probability of success, and you're going to raise it to that same K power. This doesn't look like a K anymore. You're going to raise it to that K power. Those are the 3 kids that have type O blood. And then this is the probability of failure. That's the probability of failure. And then these are the kids that are left that don't have type O blood. These are the 3 kids that do. These are the 5 kids that don't. Okay? So that formula is written on your formula sheet. All you got to do is write that formula down and tell me what the variables are. And it's not going to be that hard. The hardest part about this is getting the stupid answer, and your calculator does it. That's just the hardest part about it. If you can imagine that. Okay? Quick. Good? Happy? Click. We'll get to an example in just a second. Who cares? Who cares? How to find binomial probabilities. These are the steps you want to do to make sure you get the E. Okay? So the first thing you're going to want to ask you to do, I'm going to tell you. You tell me. It's a binomial distribution. Tell me. Binomial distribution. Tell me by one of 2 things. Name or formula. Name or formula. If you don't remember the formula, say this is a binomial distribution. If you don't want to write this is a binomial distribution, write the formula. Either one of the 2, as long as you do one of those 2, that tells the grader that you know that this is a binomial distribution. Then also tell me the number of trials by name or variable. Number of trials is N equals percent of success by name or variable. P equals, or the probability of success is 0.25. And then my probability statement, which I don't know how you write that without writing a probability statement of Px equals. There's a probability of. They will typically define the X variable for you. Okay? Clearly identified. And I don't know how you can unclearly do it, except I've seen some of your writing. Okay with that? Good? So far, step 1. So, name or formula variables. The second thing, perform the calculations. However, no work needed. So what I expect from you, what AP will expect from you is basically the values in the formula. The values in the formula. Perform calculations. Show the formula with the variables. Show the formula with the values. And you don't have to do it with the variables if you already did it up here. The way I do it is I basically write the formula with variables, and right underneath it I write the formula, or I don't really write the formula, I write the values with the formula. And that's all you need for step 1 and step 2. And then find the answer. Find the answer. And everybody knows you used your calculator or you used Desmos, because you do not want to do that by hand. We want the easiest way to get the answer, and the calculator is the easiest way to get the answer. Make sure it was the question that was asked. Answer the question. Okay, if you haven't understood anything, make sure you understand this. Recognize it's a binomial distribution. Once you recognize it's a binomial distribution, write the formula. Right underneath the formula, write the values with the formula, and then find the answer. And of course, that's what I'm going to have to show you at some point soon. Pencils, pencils, pencils. Good? Happy, happy? Click. Here we go. Genetics says that genes of children received from their parents are independent from one child to another. Each child, a particular parent, has a probability of 0.25 getting type O blood. Suppose that the parents have 5 children. Let X be the number of children with type O blood. Find the probability of X and interpret this value. A very common type question. So your job is to recognize that's a binomial distribution. And so I'm going to write the probability of X equals 3 because that's what it said. And that's the probability statement. So I've written that part. And then I'm going to write NK just like that. What does that mean? You don't care. This is telling me how many ways possible this can happen, but you really don't care. And then I'm going to put P to the K, and I'll cheat and put Q. But if you don't want to put Q, you can put 1 minus P. But Q is 1 minus P. It's understood to be that in statistics. And then you're going to put N minus K. And right underneath that, I'm going to put the probability that X equals 3. And then I'm going to put, how many kids did we have? 5 kids. So N is 5. And I'm going to put 3. And then I'm going to put 0.25. That same 3. Those are the 3 kids that have type O blood. And now I need the 2 kids that don't have type O blood. Guys, you got a P right now. That's a P without even the answer. We just got to get the answer to get me the E. Okay with that? If you leave this off or you leave this off, you don't have an E. I'm sorry, you don't even have a P. If you have one of these and the answer, you got a P. You need 3 for an E. So formula with variables, formula with values, answer. And I'm getting ready to show you that part of it. Hit me. Mm-hmm. Every time. For each kid. Okay? Each kid has a 25% chance of having success of a point. Y'all okay with that? Good? I see what she's trying to say. Wait, it's 25 and it's 75. That's not the same probability. No, it's the same probability to have type O blood. Everybody okay? Good? TI. 2 ways to do this, TI or Desmos. TI or Desmos. I'm going to tell you Desmos is probably better than TI. But I'm going to show you both. I'll show you both. Okay? So, TI. It's a binomial distribution. So you've got to go to distributions. You got to understand that part. You got to know that to know Desmos. If you don't know it's a binomial distribution, you're going to have a tough time trying to find it anywhere on any calculator. Normal PDF we don't ever use for anything. Normal CDF we use if it's normal, but this is not normal. This is binomial. Inverse normal is if you know the probability and it has to be normal, and this is not normal. And then this one's the inverse T, and there's a TP, and there's a TC, and there's a chi-squared P, and a chi-squared C, and there's an FP. I bet there's an FC right next to it. I'll be darned. There's an FC. There's binomial P. There's binomial C. There's inverse binomial. I forgot they even did that. I don't ever use that one, I don't think. Poisson, we're not using that one. Anyway, let's go back to the binomial. Now, binomials are different than normals. So let's talk just a little bit about this, because this you need to understand also. Binomials are for discrete data. You have 1 kid or 2 kids or 3 kids. You don't have 1.5 kids. You don't have 1 and 2.5 kids. All right? So binomials are for discrete data. So discrete data, you can have a PDF. You can't have a PDF for normal because that's trying to find the area of that line. And anybody that knows anything about any math whatsoever, you can't find the area of a line. You can only find area between lines. However, a PDF, a line has area because that's the probability of 1 or 2 or 0. So Way back when you were really, really young and you told mommy you had to go to the bathroom, and mommy said, do you have to go number 1 or number 2? And you told her you had to go number 1 because that was P. 1 is for the P. C is for cumulative. That's like doing both. P and P. I know, I'm not grown up. If you can understand it's the PDF, they're going to ask you for the number of trials. And how many students did we have, or how many kids did we have? We had 5 kids. 0.25 chance. And X value is 3. And so then I'm going to just go down here and I'm going to hit paste and I'm going to hit the enter, and there's your answer. There is a 8.7%, or if you want to say 8.8%, or if you want to say 8.89%, or whatever you want to say. I would not say there's a 0.909%. Now, for sure would not say there's a 0.1%. Okay with that? Of having exactly 3 kids with type O blood out of the 5. You got a question? We'll use CDF. CDF finds a cumulative. I'm going to recommend not to use CDF because that's when kids miss it. I only use PDF. Actually, I'm going to use Desmos from now on because it's easier. Actually, I don't use TI because it's archaic at best. And you can't see what it's doing. You just have to know and trust it did it right. Okay, y'all okay so far? If you guys can do binomial PDF, and it tells you, luckily it asks you the questions. I don't think anybody in here has an old 83. The old 83 didn't ask you the questions. It just looked like this. You had to do binomial PDF, and you had to put 5, and you had to put the comma in there, and you had to do 0.25, and you had to put the comma in there, and then you had to do the 3, and then close parentheses and hit enter. And nobody knew what the heck the calculator was doing, but that's what it was doing. Desmos, quickly. Not quickly, but Desmos. Desmos. All right. Typically, your Desmos, when it comes up, you type in your equation up here, but you don't have an equation, so you're going to hit the little plus sign. And you don't care about expression, and you don't care about note, and you don't care about table. You care about inference, which looks like a normal distribution. So you click inference. And over here it says probability distribution. And I want a probability distribution. And when I click it, it now says normal distribution. And I don't want normal distribution. I want a binomial distribution. There's a uniform distribution. The Desmos will actually do a uniform distribution. I didn't realize that until I saw it the other day. It says the number of trials. Dang, I keep forgetting to get my 10 key. So the number of trials was it 5 kids? 8 kids? 5 kids? 5 kids. 5 kids. Tab over to the success of probability, which is 0.25. And then it asked me to create the distribution, which is a whole lot nicer because look, I can see the 0 and I can see the 1 and I can see the 2 and the 3 and the 4 and the 5. So that shows me all 5 possibilities. Actually, I should say all 6 possibilities. 1, 2, 3, no, 5 possibilities. Oh, 6. 1, 2, 3, 4, 5, 6. 6 possibilities. 0 kids, 1 kid, 2 kids, 3 kids, 4 kids, or all 5 kids. What are the best chances? 1 kid. Which should somewhat make sense because there's a what? 25% chance that one of them has it. And if I got 5 kids, out of those 5 kids, one of them should have it. If there's a 25% chance. In fact, out of 4 kids, one of them should have it. But they wanted what? How many kids? 3? So I'll just highlight the 3, and there's your answer. There's your answer. If you wanted 4, you can see 4 really easily. And there's 5, and there's 2, and there's 1, and there's 0. And it gives you all of them pretty quickly, a whole lot better, I think, than TI does. Plus, it actually shows you the picture. Yeah, a little bit better. Get comfortable with both, I recommend, because you may, one of them may decide to blink out on you one day. But I hate to push Desmos, but better than TI on this part for sure. Yes, no, maybe. All okay? All right, let's keep going. Let's keep going. Apply, slideshow. Boom. Here's where they wrote it out in words. Guys, if this was a free response question, I want to make sure I'm going to get my points. X is a binomial random variable. X is a binomial distribution. N equals 5. P equals 0.25. Do you have to put all that? No. If you have the formula by itself and you put the values underneath it, we can read all that. And if you got that weird looking formula thing, we know it's binomial. If you write the words, it really helps. You don't have to write this step here. However, I do think it's important to note, what is that 10 telling me? There are 10 ways for this to happen. There are 10 ways for this to happen. It could be the first 3 and the next 2, or the first 2 and the third and the next, right? There's 10 ways for that to happen. I do think it's important that you understand that, but I don't think you need to write that. There is about a 8.8% chance that exactly 3 out of the 5 have type O blood. Yes, no, maybe? Several pencils are going right now. The hardest part about well, there's 2 things hard about it. Recognizing it's binomial. And this isn't that hard because what? Well, that's the section we're talking about. But picture yourself in May having to try to recognize if it's binomial. And then the third hardest part, I think, or the second hardest part, is finding that answer, which is not that hard, except you got to try to remember how to do that in May. Most people can understand. Once you see it's binomial, you're going to write the formula. You're going to write the values. You just got to find the answer. And everybody knows you're going to use your calculator. So you don't need to say, I use my calculator. I know. We know. You don't have to state the obvious. Should I be surprised if more than 3? All right, so this again is where you got to start understanding some of this stuff, guys. I want the probability. Watch what I'm going to do here. This is scary. If I want more than 3, right? More than 3. That means what? 4 or 5. So here's what I want you guys to recognize, because this is a possible type scenario. They might say this. Y'all see those 2? They better be the same answer. And that's something you need to recognize for multiple choices. Because in discrete distributions, greater than or equal to 4 is the same answer as greater than 3. In normal distributions, it's not. Because this one starts at 4 and goes out. This one starts at 3 and goes out. And there are values between 3 and 4 for continuous distributions. If you can start, if you start putting all this together, man, we're doing good. Okay with all that? So I've got to do one of 2 things now. I've got to go to Desmos and find 4 and find 5 and add those 2 together. Or you got to do PDF of 4 and do PDF of 5 and add those 2 together. Okay? Just to kind of show you on your calculator, you can do all that in one step. If you do it in Desmos, you got to look at 4, then you got to look at 5 and just add those 2 together is one way. I'll show you a different way too. A calculator, right? So I can do binomial distributions. It's alpha A. 5 trials. I need 4 kids. Okay? Paste it. And then I can hit plus. And now I'll do all 5 kids. Second distribution, alpha A. Oops, what happened there? Quit. What the heck is going on? Go to the end. Okay, here we go. Second, distributions, alpha A. I don't know what happened there. 5 kids? Yes. 0.25. All 5 kids. Paste it, and those are going to add those two together. There's like a 1% chance, a 1.5% chance that 4 or 5 kids will have type O blood. Let me show you Desmos again. Also, besides the point of just adding those two, which you could just add those two, you also can go over here to cumulative probability. Inner, I don't want the inner, and I don't want the outer, and I don't want the left, I want the right. And it says X greater than or equal to, so that's where you need to recognize I got to put a 4 there. I can't put the 3. And so I'll put a 4 there. 4. And there it is added together already for me. 0.01562, which is what we got with the binomial PDF. You'll get practice on this on your homework. Practice, please, guys. Practice. Practice. Get comfortable with that calculator. Get comfortable with Desmos. Either one of the two. Preferably get comfortable with both. Because you never know what might happen later on. I don't think I've seen issues with Desmos, but it hadn't been around that long. Now, I still didn't answer their question, guys. Because what was their question? Should the parents be surprised? So what was the chances of getting 4 or 5? 1%? Should I be surprised? Because that number is what? Less than 5. Because that number is less than 5, I should be surprised if 4 or 5 of my children got type O blood. Okay? If it was over 5%, I still might be surprised, but I shouldn't be totally surprised. That 5% is that kind of that model that we look at. Again, they probably showed a whole lot more than you will. You don't have to show everything that they showed. Okay? How I would show that, just let me show you how I would show this step, right? I would go 5, 4, 0.254, 0.751, and then just put plus 5, 0.255. And then you can put 0.750, but 0.750 is 1. Okay? So, show your step, show something, don't give a completely naked answer. Bunch of pencils are going. Question, question, question. Recognizing it's binomial is tough. Finding the answer is tough. And if you don't think either of those are tough, then we're good. Hopefully you don't think they're tough, and then you're going to be good. Clicky, click, 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 click. Boom. Here's the instructions on how to do it on your TI-84 if you needed it to, right? Here's binomial PDF. Binomial PDF does count a single binomial. Sharlika already asked, so just be aware, if you want to use CDF on your calculator, it only goes from 0 up. And that's why I don't like it. Because if you want 4 or 5, it's easier, I'm telling you, it's easier to do PDF of 4 plus PDF of 5. Because your calculator only goes from 0 up. So let me kind of show you what I mean by that, right? You have 0, you have 1, you have 2, you have 3, you have 4, you have all 5. These are the 2 that I want. Well, your calculator only goes from 0 up. That's why I like Desmos, because you can do 4 or higher. But if your calculator only goes from 0 up, you've got to go from 0 to 3 and subtract that from 1. And that's where students messed up. That's just where they messed up, because they don't see a 3, or they're trying to figure out, why am I taking away 3 if I want more than 3? Well, if you want more than 3, you don't want the 3. It just starts to become messing with your head a little bit. And that's why I recommend Desmos. Desmos, you don't have to worry about only doing to the left. Okay? Problem number 2. Let's get away from the blood type. A local fast food restaurant is running a draw a 3, get it free lunch promotion. So you're going to go to lunch and you're going to get a random generator card. If the 3 shows up, you get it for free. If a 3 doesn't show up, you have to pay. Press here to win a free lunch. A computer program then simulates one card being drawn from the deck of cards. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. On the first day of the promotion, 250 customers placed lunch orders. Find the probability that fewer than 10 of them win a free lunch. So you got to recognize that each one is independent of the previous. You got to recognize you got a fixed number of trials. You got to recognize that the probability is the same every time of winning, because I'm using a computer program and I have a 3 out of 52 chance of winning. I have a 48 out of 52 chance of losing. I want the probability that fewer than 10 win. This is careful. I want the probability that X is fewer than 10. So you can either put less than 10, or you can put less than or equal to 9. Those are the type of things you have to understand about this lesson. Less than 10 is the same thing as less than or equal to 9. Because Desmos only does less than or equal to, or greater than or equal to, I'm going to do that. Okay? Equals. And then I'm going to put the 250. And I'm going to put 0. Because I'm going to start at 0. And then I'm going to put a 4 out of 52 chance of winning. However, I don't want any of them to win, so that's going to go to the 0 power. And then I want 48 out of 52 to win, and to lose, and I want all 250 of them to lose. Holy cow, are you going to make me write the 1 and the 2 and the 3 and the 4? No. We're getting ready to put plus and a dot and a dot and a dot. That way we don't have to write them all, because there's no reason to write them all, because it's just the same thing over and over again. However, I'm going to write it up until, and I'm going to put a 250. And I messed up the very first time I did this class, because I put a 10 underneath here. And I don't want the 10. That's why I like to put it that way. I want this to be a 9. Okay? And it's little things like that that are going to ding us down from our E's to our P's. So that needs to be a 9. We still want 4 out of 52 to win. However, I want 9 of these guys to win. And I want 48 out of 52 to lose. And out of 250, that's 241 to lose. Okay with that? I'm letting you guys write down and soak that in. Any questions about the notation or something else? Recognizing it's binomial, writing the steps down, and now we're going to go to our calculator to do all the work. So we can do this in calculator, or we can do this in Desmos. Let me show you the calculator. The calculator is not bad because it is a less than. So I would go binomial distributions, and I would go with CDF this time. There are 250 trials. There is a 4 out of 52 chance of winning. Remember, it was a 3 out of the deck of 52 cards, so there are 4 3s out of the 52 cards. And I want 0 to 9. 0 to 9. .006. Not a very good chance. Let me show you in Desmos really quickly. Again, I think I like it just a little bit better. I'll get out of this one. I'll just close it. Hit my plus symbol. Go down to inference. Probability distributions. Normal. Change it to binomial. Trials are 250. 250. Tab over. 4 out of 52 chance of winning. Create the distribution. There's the distribution. I want the cumulative probability. I want the left. I don't want the inner. I don't want the outer. I want the left. And I want it less than or equal to 9. And that gives me that same 0.006128. Everybody good? Practice this on your homework, and you should, I hope we're okay. I hope we're okay. Oops, I don't want that. You get back up here. All right, I want this. Apply. Slideshow. Boom. Here's that same 0.00613. They wrote binomial CDF. I don't like calculator talk. It's not wrong. I just don't like it. If you want to, you can. I just soon you write the formula. It just looks better. It just looks like you know what you're doing more rather than you know what to do in the calculator. All right. In fact, only 9 customers won a free lunch. So out of those 250, only 9 won. And the chances of only 9 winning or less was like almost 0%, like less than 1%. Does this result give convincing evidence that the computer program is flawed? Yeah. Yeah. Because that probability is less than 5. If the computer program was running correctly, we should have had more people win than 9. It should not have been only 9 winners because the chances of only 9 or less is like 0.001. It's like a really, really small chance, and it actually happened. That computer's jacked. Or there's 250 really unlucky customers, or I guess 241 really unlucky customers. Y'all okay? Click. There's only a 0.00 probability chance that fewer than 10 customers would win, or 9 or fewer, if the computer program is working properly. Because only 9 customers won, we have convincing evidence that the computer program is flawed. If that number was bigger than 0.05, we don't have enough evidence. Even though it's still a small chance, we think 5% is still a chance it can happen. Soak that up. Again, try to picture yourself. Finding that answer is not necessarily the hardest thing about this lesson, right? Knowing what that answer found us and what is it telling us starts to make this a little bit more difficult. Bunch of pencils. How am I doing? Oh man, I'm doing good. Doing good. We got 3 more concepts we got to cover. 3 more. All right, children. Clicky. Oh, I'm sorry, I lied. I'm sorry, 4. I need to tell you the mean of a binomial distribution. They might ask you for the mean, and the mean is simply, gotta have a writing utensil. The mean of a binomial distribution is simply n times p. It's n times p. That's on your formula sheet, right? If you're having 5 kids, 5 times 0.25, you should have 1.25 or 1, I think it is 1.25 kids with type O blood. If you wanted the mean of this distribution, you would take 250 and multiply it by 4 out of 52, and that should tell you how many people should win a free lunch. Mean, simple little formula, okay? Standard deviation is almost as simple. The standard deviation, if it's a binomial distribution, is equal to n times p times 1 minus p. Just a plug and chug formula. I have not seen them ask for the mean or the standard deviation very much. Those are on your formula sheet. If they ask for it, it's just a plug and chug. What is the mean and what is the standard deviation of the binomial random variable? So here's one to ask you to calculate the mean. You got 21 students and 1/3. So you multiply 21 times 1/3, it should be 7. To find the standard deviation, you take 21 and you multiply it by 1/3 and you multiply it by 2/3 and you take the square root. 21 times 1/3 times 2/3, take the square root, 2.16. I didn't want to spend a lot of time with that. It's plug and chug. You may or may not see it. And if you do, it's plug and chug into the formula. It's on your formula sheet. Of course, they'll ask you to interpret. Typically varies from the mean, right? You guys are getting pretty good at that, I hope, by now. Seen it quite a few times. All right, now, let's learn a little bit more. Most real-world scenarios, you do not replace. Once you select a student, you really don't put that student back in because you don't want to select that student again. Y'all okay? Most real world scenarios, once you select, you do not put them back into the population. Well, if you don't put them back into the population, what have we done? We have violated the independence rule because we have now changed the probability of the next person being selected. Okay with that? So here's what statisticians have said. Most real-world sampling, such as taking an SRS from population history, is done without replacement. Sampling without replacement leads to a violation of the independent condition. However, this is what they say. When the population is so big, okay, when it's so big, and I'll tell you how much bigger it needs to be, it won't matter if you don't put them in. In other words, if I'm taking one student from this school and there's 3,800 students in this school, if I take one out of 3,800, now I'm taking one from 3,299, 3,799. I don't think it's that big of a difference in chances of being selected. Fair enough with that? And because that population is so large, it doesn't really matter if I put them back in or if I don't put them back in. Whether the population is much larger than the sample in SRS, it has an approximate binomial distribution. When taking a random sample from the population of size n, we can use the binomial distribution, provided this, and it's called the 10% condition. And this is about the time in the year where I got to start beating this condition in your heads. You want your sample size, whatever your sample size is, whatever you decide your sample size to be, you want that to be less than 10% of the population. You want your sample to be less than 10% of the population. And what that's going to do, guys, is not care if you put them back in or not. That replacement won't matter for two reasons. One, it's not going to change the probability very much. And two, even if I put them back in, the chances of getting them are almost small. They're really small. So when your sample size is less than 10% of the population, it doesn't matter if you replace them or don't. How are you going to know? It's going to be common sense. It's going to be common sense. I'll show you in just a second how you know. Everybody okay? Follow? Condition you got to know. We got a survey of 500 U.S. teenagers, ages 14 to 18. Did it say where these 500 U.S. teenagers came from? United States. Okay with that? Subjects were asked a variety of questions about personal finance. One of the questions asked, do they have a debit card? Yes or no? Success, failure. Exactly 12% of these have debit cards. Same probability. Probability stays the same every single time. The number of teens, let X be the number of teens of a random sample of 500. Explain why X can be modeled by a binomial distribution even though the sample was selected without replacement. I bet there's more than 5,000 U.S. teenagers. There's almost 5,000 in this school, right? Guarantee it, between us and West and Rogers and Fayetteville, we got 5,000 kids, and we didn't even leave Northwest Arkansas. Okay with that? And all we have to say is because 500 is less than 10% of all U.S. teens. And I always get somebody like, how do you know? I'm pretty smart. I know there's more than 5,000 U.S. teens. I take a random sample of 200 pine trees. I bet there's more than 2,000 pine trees. Everybody okay? Kind of makes sense? That's a condition, guys. It's going to stick with us for the rest of the year. It's a condition you have to check all year long. Okay? Y'all okay with the 10% condition? Here it goes. 500 is less than 10% of all U.S. teenagers, ages 14 to 18. Okay? All right. Now then, use a binomial distribution to estimate that 50 or fewer have this. Okay, so we can plug and chug that into my formula. 0 to 50, yada, yada, yada. I don't want to do all that stuff. It's binomial CDF. There's a 9% chance. It's okay. You guys are going to get practice on that on your homeworks. Okay, now then, look at this. This is a binomial distribution with n being 10 and p being 0.8, skewed to the left. Notice it's closer to the 8 range. Here's binomial 28. Now it's closer to the 16. It's still skewed to the left, but not by a whole lot. When n becomes 50 and it's 0.8, now we're really close to a normal distribution. So here's the next thing I want you guys to know. It's called the large counts condition. And guys, if it meets the large counts condition, you don't even have to do a binomial distribution. You can use a normal distribution, which you guys are a whole lot more comfortable with. So here's what the large counts condition says. As long as n, what is n? That's my sample size. As long as my sample size times p, and p is the probability of success. If n times p is greater than 10, they say it's okay to be equal to. I don't think I've ever seen it equal to. Not only this has to happen, n times q also has to be bigger than 10. If both of these happen, I can use a normal distribution. If those happen, I can use a normal distribution. I don't even have to use a binomial. What if I do? You'll get almost the same answer. Are they both accepted? Yes. Yes, they're both accepted. What if n times p is not greater than 10? You better not use a normal distribution. You better use a binomial. If n times p and n times 1 minus p are both greater than 10, and it's still independent, and it's still the same probability, and you still have a fixed number of trials, you can use binomial or normal. Good enough? It's a lot of information on this chapter or this section. A lot. I don't know how much hard it is, but man, it's hard to get it all in your head. Because it's a lot of tying a lot of stuff together. Click. Here's my US teenagers. 500 of them. 12%. Justify why X can be used a normal distribution. Well, it's telling me that it can. So my guess is N times P, I'm going to bet that number is bigger than 10. 10% of 500 is 50. 12% of 500, I think, is 60. It is. But now I got to check the other side of that too. 500 times 88%. Well, if that's 60, this has to be 440. And both of those are what? Greater than 10. And so because they're both greater than 10, I can use a normal distribution. And this is where the mean and the standard deviation come into play, because you got to know what the mean is and you got to know what the standard deviation is. And you learned the mean just a second ago. It's N times P. And this is N times P times 1 minus P square rooted. And so now you have a normal distribution with a mean and a standard deviation, and you can use normal CDF instead of P CDF. Wowzers. Wowzers. What questions does someone have? Click. There we go. Now it tells me to use a normal CDF or use a normal to find 50 or fewer. And so because I'm using a normal distribution, I need to know what the mean is, which is 60. I need to know what the standard deviation is, which is 7.266. I need to draw a normal distribution with that mean and that standard deviation, and I want to go to the left of 2138. This should be negative 1,000. I want to go to the left of 2138. And so I'm going to go from negative 99999 to 2138. And no, 2138 is the Z. That's supposed to be negative 2. That's the Z score. You don't want to do that. You want to go to 50. Sorry. You want to go to 50 with a mean of 60 and a standard deviation of 7.2. Focus on this homework. It's a doozy. It's a doozy. Last thing. And I don't do geometric. I don't do geometric. Here's what geometric will do. It's a binomial without a fixed number of trials. You're waiting for it to happen. You're waiting for it to happen. What's the probability that exactly 1 of the 5 children have type O blood? Suppose we're not interested in the type of O blood out of 5, but I'm interested in the first kid that has type O blood. Okay? I'm interested in the first kid that has type O blood. Well, what's the probability that the first kid had type O blood? 0.25. There's a 25% chance that the first kid had type O blood. What's the probability that the second kid had type O blood? Well, if it's the second kid, what does that mean about the first kid? It didn't have type O blood. Okay? What's the probability of the third kid? Well, that means the first one didn't, and the second one didn't, and the third one did. You kind of with me on that? So I could actually, because you guys are freaking brilliant, what's the probability that the first one is the 10th one? that means we didn't have one, and 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 we didn't have one for 9 times, and then we finally had the kid with type O blood. You'll kind of follow that? I don't use geometric settings. I just use independent rule from previous chapter, which I think is easier than the independence. Not success. Okay with that? Geometric sign when we don't have fixed number of trials, just kind of recognize that. You don't have a fixed number of trials. I will say that geometric settings are going out of AP next year. They are not even going to be in it. I don't think they're going to be much in it now. That's what I'm going off of. They're not on my test. 40% have type A blood. I'm at a worker at a blood bank and I need type A blood. I want to figure out how many blood donations I have. Well, what's the probability that the first one has type A blood? 40%. What's the probability that the second one? 0.24%. Wait a second. What do you mean? The second one's less than the first one? Yep. What about the third one? It's even less. Why is it the less? Because that's the probability it happens the first time. Like, it should have happened by now. By the time I get to the fourth kid, I should have had a type A blood. And if I hadn't, the chances of it happening now, or I don't want to say better, because they're not, but the chance of it happening by now are pretty low because it should have already happened. Failure to n-1 success. Again, I don't worry that much about it. You'll see a couple on your homework, but I think it's just easier just to use your independence rules. Okay. Find the probability the class receives exactly 10 homework problems. So we do. Beautiful, beautiful. I don't use it. There is a formula for the mean of a geometric. It's 1 over P. It's on your formula sheet if you need it. There's the standard deviation. So here's the mean. Why do they do that? I don't know. There's the mean. It's 1 over P. And then the standard deviation is 1 minus P rooted over P. Like I said, you might see a homework question. I'm not even going to ask you a test question over geometric. I'm not even asking a test question over geometric. Boom, boom. This is what a geometric distribution looks like. Geometric distributions are always skewed to the right. Binomials are not. Who cares? Who cares? Who cares? Who cares? All right. Let's see if we make sure, guys, make sure you guys understand these things. Determine if the conditions for a binomial are set. Do you know it's binomial or not? You got to be able to recognize that. Calculate and interpret the probabilities of a binomial distribution. So hopefully you can calculate and find those probabilities. I hope you can calculate the mean and the standard deviation of a binomial distribution. That's really easy because that's just a plug and chug. I hope you can use the normal distribution if it's appropriate. If it's appropriate. If n times p and n times 1 minus p are greater than 10, I can use a normal distribution. Calculate and interpret the probabilities of a geometric random variable. Calculate the mean and standard deviations of a geometric random variable. I did not do a very good job of that, but I don't think it's that important, and that's why. You got enough information from here to here that I don't think it's that big of a deal. I haven't had anybody complain yet. However, if we get to one of those questions where most people missed it, it's probably not a you issue, it's a me issue. Clicky, click, 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 click. Please, please, please focus on this lesson. It's not a doozy if you do it, but if you don't do it, of course, duh. Or if you just hobnob through it or just try to get your answers, it's a bad deal.